Thank you very much, Luisa. Good morning. Indeed, I'll try to present you recent results about propagation of fractures in heterogeneous materials. I will not talk about any fracture, but the fastest possible fractures in such materials, which means fractures that propagate at speeds that are comparable to the speed of sound in the material. And as the material is heterogeneous, in some conditions, these cracks can propagate together with their own damage zone, which is made of a cloud of microcracks. And the scope of the talk will be to understand how these microcracks can interact with the main crack, and how they mainly control its macroscopic properties, dynamics. So I will first begin with an experimental study made during the PhD of Claudia Guerra, in collaboration with Daniel Bonamy from CEA Saclay and David Almas from CNRS in France. And I will finish with ongoing simulations of a frictional system performed by Christopher Hawkins in collaboration with Anders Malte Sørensen. So first, let me convince you that these fast cracks are not just exotic objects that physicists can create just for fun's sake, but at least they exist in nature. And I took two examples for you. First, earthquakes that are often very fast fractures at a seismic fault can propagate up to velocities close to the speed of sound in the surrounding rocks. And this can be demonstrated either by dynamic inversion of seismograms, but also directly by looking at rocks, like this example of the Adamello intrusion, in which the asymmetry and the angles of such pseudo-tachylite veins around the main fault indicate that the velocity at which this fault broke is close to 0.9 times the shear wave speed in the surrounding rocks. Another example is when you have a large impact by a comet or a meteorite in the surrounding rocks. You can have secondary branching fractures creating the so-called shatter cones, like this one, taken from the Vredefort site in South Africa. And by studying the angles of the striations that we can observe on these shatter cones, we can demonstrate that these were formed by the propagation of a crack that is very close to the velocity of the Rayleigh speeds in the material. And the Rayleigh speed, for those who don't know, is the velocity of waves at the free surface of the material. So now, to get some more fundamental and quantitative insights into these fast cracks, I will focus the rest of the talk on laboratory experiments on analog materials. So let's consider material fractures in opening mode, and let's have a look at the side of the sample when it's broken. This is for PMMA, and when the velocity is high enough, then you can observe on the side of the sample these characteristic lines, which corresponds to aborted secondary crack branches. And in this plot of the branch length as a function of the velocity of the crack, you can see that these micro branches onset at a very well-defined velocity, around 0.36 times the Rayleigh speed in PMMA. These cracks are not single cracks as soon as they go very fast. And even the most brittle or nominally brittle materials like PMMA, at even slower velocities, they are not single cracks, because they exhibit micro characteristic patterns that we will see later on in the talk, conic-like patterns that are characteristic of micro cracks opening ahead of the main crack and coalescing with a front. And here, on this plot of the density, surface density of such micro cracks as a function of crack velocity, you can see that they also onset at a very well-defined velocity, around 0.2 times the Rayleigh speed. So fast cracks are almost never single cracks as described in the standard fracture mechanics theory. So in the rest, I will focus on the role of microcracking in this quasi-brittle regime in which you have this cloud of microcracks around the main crack. So for this, we did experiments. And So we consider a decimetric sample of PMMA or plexiglass, which we prepare with a seed crack here. And then we load the sample in tension by slowly introducing a wedge between two jaws here. And at a given force, a threshold force, then a crack nucleates and propagates very fast across the sample. And in this geometry, the crack is very stable and cuts the sample into almost equal two halves. By adjusting the radius of this hole, we can adjust the initial velocity in the system through the energy, the elastic energy stored before cracking. So what can we do during this experiment? First, we can measure electrically the macroscopic velocity of this crack as a function of crack length. And this measure allows us to have values for this velocity up to 500 meters per second with a pitch of 1 millimeter along the crack length and an accuracy that is better than 10%. Another thing that we can obtain is the value of the so-called stress intensity factor K, which relates the local stresses at the crack tip to the distance to the crack tip through this characteristic 1 over the square root of the distance divergence. And this is done by finite elements. So with these two quantities, for a given location along the crack path, we are able to ascribe a macroscopic velocity and a local stress intensity factor, which will act as control parameters in the rest of the talk. So now, observations. When we broke the sample, we look at the fracture surface, and depending on the velocity at which it broke, we can find different patterns. At low velocity, below VA equals 160 meters per second, the fracture surfaces are essentially smooth. But above this threshold, as I told you before, there are the appearance of these conic-like markings with surface density that is increasing with crack propagation speed. And these markings are classically interpreted in this very simple geometric model. So consider a straight crack that is propagating rightwards towards a defect in the material located at its red cross. When it reaches a distance dm from the cross, this defect turns into a microcrack that grows radially on its own. And then when the two fronts coalesce in space and time, they leave a visible mark on the fracture surface that is along this red line. Of course, when you have more defects, you have interaction between different microcracks, and you can obtain such complicated patterns. And here is just a movie to show you that it's easy to simulate this kind of geometrical processes. Here are 3 defects with all the same triggering distance dm and all the same growth velocity. So now the idea is to take a real pattern observed in the experiment and to try to reconstruct the processes that led to this precise pattern. So to do that, we rely on fractography. We just study the patterns on the fracture surface. So we can, the aim is to find the parameters that are necessary to feed the geometrical model. So the first thing we do is to locate on such images the centers of nucleation for the microcracks. We do that using, for example, this white zones in the images. And then we can have some information about the statistics of the locations of these centers. And we found that they are distributed on the plane randomly, homogeneously with no correlation, which is typical for a Poisson process in 2D. And this Poisson process is characterized by only one parameter, which is the mean density of points per unit space, which I will use as a control parameter for the rest of the talk now. So given velocity or stress intensity factor will correspond to a given value for this rho density. And of course, we can calibrate the evolution of rho as a function of the stress intensity factor, for example.
Doesn't it depend on the material?
I guess so, but I only studied PMMA up to now. So I cannot answer that. So, okay. Okay. So the other thing we can extract from the images is when we consider a given couple of centers, using the framework of the geometrical model, we can fit the line in between. Here's this green line. In order to extract one quantity that is the only fitting parameter in the procedure, which is the ratio of the velocities C2 over C1, gross velocity of the second microcrack divided by the one of the first one. And again, if we do that for a lot of couples like this, we can find the cumulative distribution, for example, of this velocity ratio. And we find that for different values of rho, they all have a typical Gaussian distribution, which is centered around 1, and which is very narrowly distributed with a standard deviation as low as 0.02. Which means that locally, microcracks propagate at the same velocity. One and the next one propagate at the same velocity. And this is the assumption we will make for all the rest. That C1 equals C2 equals a constant we call Cm. Now, in these conditions, when the velocities are equal, then these lines are true mathematical conics. Which means that we can have an easy graphical estimation of the triggering distance here. The distance between a center and the triggering front at the instant of nucleation, which is just twice the distance between the focus of the conics and its apex. So for each microcrack, we can measure like this the triggering distance. Let me go back, just show you quickly the statistics here. And this quantity is also characteristic distributions that we found to be a two-parameter quadratic distribution for which we have no real explanation right now. And here we calibrated the mean distance at nucleation as a function of rho, the nucleation center density. And we have two regimes here, a linear, quasi-linear increase, followed by a plateau, and the transition here corresponds in the experiment to the onset of the micro-branching instability. Okay, so now we have all the ingredients we need to feed the geometrical model and to apply it to a real image like this one. We locate all points, then we measure all nucleation distances, and we assume that all grow at the very same velocity. And we obtain this pattern in red, which, if you look in detail, corresponds very nicely to what is observed in the fracture surface. So this quality validates both the geometrical model and also our image analysis in order to get a pattern. And of course, we don't have only the final state, but also all the time dynamics in between, so leading to this pattern. As we can see here, there is a main crack front propagating, and ahead of it, you have the nucleation of small microcracks that grow individually and then are taken over by the main front and coalesce with it. So it's this a deterministic reconstruction of both the microscale crack growth, but also the associated damage through this cloud of microcracks. And I emphasize that we have resolutions of around 1 micrometer in space and 10 nanoseconds in time simultaneously. which is not accessible by any experimental means today. Okay. So now let me change scales and come back to the macro scale in order to understand the role of microcracks in the macroscopic velocity of the sample. So in this plot, you can see the front position as a function of time for 3 different microcrack densities in the simulation. So when there is no microcrack, of course, you have a linear increase because everybody grows at a constant velocity. Then you have an effective slope for this increase that is increasing with rho. And why is that slope increasing? Well, and if you zoom on this curve, for example, you can see that it's made of linear increases plus a series of jumps that corresponds to coalescence event with microcracks. And of course, the more microcracks you have, the more coalescence events you get, and so the higher the effective slope of this curve. So now, if you consider this as an effective velocity, apparent velocity for the crack, and you divide it by the local macroscopic velocity, then you are defining an acceleration factor of geometric origin for the role of microcracks. And this is the evolution of the acceleration factor, a function of density of microcracks. Of course, when there is no microcracks, this acceleration is 1, and it can go up to 2 in the experiments that we analyzed. Very quickly, we built a 1D model to understand the evolution of this acceleration factor as a function of the density rho and also the triggering distances. We found this dependence, and it works very well with the simulation results in here. Here, the change in regime corresponds to the change in regime we saw for the triggering distance when the micro branch is onset. So finally, we want to have a real value now for the macroscopic growth rate of microcracks. And to do that, we simply divide the experimental velocity that we measured by the acceleration factor that we extracted from the simulation. And doing that, we find all these points as a function of nucleation center density, and it's a remarkably constant value, around 217 meters per second. A constant here means independence with respect to the local loading, the stress intensity factor K, so that we can say that this macroscopic growth rate is a material constant in practice. So, just to summarize this part, a sketch of how the macroscopic crack velocity here is selected when you know the local stress intensity factor. Well, what we saw is that this stress intensity factor actually controls 2 internal variables that are valid at the microscale: the microcrack density rho and also the mean nucleation distance here. These 2 local quantities combine into a geometric acceleration factor A, and when multiplied by the local crack velocity Cm, we can recover the final macroscopic velocity. Of course, there are a series of open questions. This is connected to your question. We did that for one material, but actually we don't even know what's the real origin of the microcracks in the sample we used, which is plexiglass. These are some AFM pictures of the nucleation centers that suggest that there could be cavitation at the origin of these microcracks. About the generality of these results, microcracks and the patterns related can be observed in oxide glass and mainly in other polymeric glasses like polystyrene or polyurethane. And we would like to understand in the future if we could understand these patterns in the same way we did for PMMA. Of course, how does the local cracking velocity depend on the material is also something which is mainly open. On this, I would like to thank you for your attention and advertise an opening experimental PhD position in France, in my lab in Ecole Centrale de Lyon, about precisely these dynamic ruptures in frictional interfaces that are heterogeneous. Thank you very much.